Hey everyone, and welcome. Today, we're diving into the unsung hero of our digital lives, quality of service, or QoS for short. It's that invisible magic that keeps your Zoom calls from freezing and your online games from lagging even when the whole house is online. So let's jump right in.
You've definitely been there, right? You're on a super important video call, and boom, your boss suddenly turns into a blocky, pixelated mess. Or maybe you're about to win a game, and your connection just dies. So what is actually going on behind the scenes during those moments of pure digital frustration?
Well, the culprit is the internet's default setting, which is basically best effort. Just imagine a highway with only one lane for everybody. It doesn't matter if you're an ambulance rushing to the hospital or a giant truck hauling non-urgent cargo, everyone is stuck in the exact same traffic jam. On the internet, that means every single piece of data, whether it's your video call or just a background update, gets treated with the exact same, non-existent priority.
So what happens when that one-lane highway gets totally overwhelmed with cars? You get a massive traffic jam. And that's the core problem we call network congestion.
When way too much data tries to cram through a single point at once, a few really bad things happen. First, some data packets just get dropped, vanished. That's called packet loss. Other packets get stuck waiting in line, which causes delays, or what we call latency. And maybe the most annoying one for video and voice is jitter. That's when packets arrive all out of rhythm. This terrible trio is exactly why a clear call can turn into a garbled, robotic mess in seconds.
Okay, so if the problem is a single-lane highway, the solution seems pretty obvious, doesn't it? We need to build some express lanes. And that is precisely what quality of service does for our data.
At its core, QoS is really just a set of rules that tells the network which traffic is important and which can wait. Think of it like the ultimate traffic cop for the internet. It looks at every piece of data and decides you get to zoom ahead in the fast lane, and you can just cruise along with everyone else. It's all about recognizing that not all data is created equal.
Now, the main system that networks use to actually build these digital highways is called differentiated services, or DiffServ. This is the master plan, the architecture that creates a system to classify and mark every single data packet so that all the routers along the way know exactly how to handle it.
And you know, this system is unbelievably flexible. Tucked away inside the header of every IP packet is a tiny 6-bit field called the Differentiated Services Code Point, or DSCP. Now, with 6 bits, you can create up to 64 different classes of traffic. That's like having 64 different kinds of express lanes, each for a very specific job.
And here's a quick look at how this plays out in the real world. Voice traffic, which is super sensitive to even tiny delays, gets the absolute highest priority. It's marked as EF, for expedited forwarding. Right behind that, you've got video conferencing. Then comes your regular stuff like web browsing and email, which gets the default best effort treatment. And way down at the bottom are things like big file transfers, which can happily chug along in the background without getting in the way.
Okay, so we've got our express lanes all mapped out. But how do we actually control the flow of traffic to stop jams from happening in the first place? Well, this brings us to two really important tools in the QoS toolkit: policing and shaping. First up is traffic policing. Think of it as a really strict bouncer at an exclusive club. It sets a hard limit on how much traffic gets in. If a sudden flood of data shows up that's over the limit, the policer just drops the extra packets on the floor. It's kind of harsh, yeah, but it's a really effective way to tell the sender, hey, you need to slow down, now.
Traffic shaping, on the other hand, is a bit more polite. Instead of just dropping the extra packets, it puts them into a temporary holding area, a buffer, and then lets them out at a nice, steady, controlled pace. It smooths out those sudden bursts of traffic. The only catch? That buffering adds a tiny bit of delay or latency, but the big advantage is that it avoids dropping packets like policing does.
So let's put them side by side. Policing is the bouncer. It discards extra packets. Shaping is the polite host. It buffers them. Policing can work on traffic coming in or going out, while shaping is really just for outbound traffic. So at the end of the day, you police traffic you want to strictly limit, and you shape traffic you want to smooth out before sending it along. All right, building on those tools, let's see what happens next. So once the traffic gets past the bouncer, how does a router decide which data to send out first when things get crowded? That, my friends, is where queuing comes in. The whole process is actually pretty logical. When a router's exit gets congested, it doesn't just throw all the data into one big messy line. Instead, it sorts everything into different queues.
based on those DSCP markings we talked about. All the voice packets marked EF go into the special VIP queue. The router then serves that queue first, sending every single voice packet out before it even glances at the others. This is how our digital ambulances get to blow right past the traffic jam.
So we've figured out how to handle delays, but now we got to solve that other super frustrating problem, the one that makes people sound like robots and makes video all choppy. Let's talk about jitter.
So what in the world is network jitter, anyway?
To put it simply, jitter is just inconsistency. See, in a perfect world, data packets that are sent 20 milliseconds apart would also arrive 20 milliseconds apart. But thanks to network traffic jams, they might arrive 10 milliseconds apart, then 30, then maybe 25. They're totally out of rhythm, like a drummer who can't keep a beat. And your computer has no idea how to piece that mess together into something smooth.
The solution here is a really clever tool called a jitter buffer. You can think of it like a shock absorber for your data. As the packets arrive all out of sync, the jitter buffer collects them and holds them for just a fraction of a second. This tiny, intentional delay gives the late packets a chance to catch up. Then your device can play them all out in a perfectly smooth, evenly spaced stream. It's an amazing trick. You trade a tiny, unnoticeable bit of latency to completely get rid of that awful, jarring jitter. Okay, so we've gone through express lanes, bouncers at the door, priority queues, and shock absorbers for our data. Let's bring this all home and look at the real-world impact of all this tech. Honestly, the difference is like night and day. On a standard best-effort network, every app is in a chaotic free-for-all, fighting for bandwidth, which just leads to lag and terrible performance. But on a network with QoS enabled, it's a completely different story. Critical applications get the priority they need. Your video calls are crystal clear, your gaming is responsive, and those huge file downloads just happen quietly in the background without wrecking everything else.
And that really is the heart of it all. QoS isn't about making the internet faster. It's about making it smarter. It's about making sure that the apps that truly need consistent, reliable performance actually get it. And that creates a way better experience for all of us.
And that leaves us with a really fascinating question to think about. We've built this incredible system for prioritizing data, but in a world that now runs on real-time communication, on Zoom calls, remote work, and constant streaming, who should get to decide what's important? Who gets to set the rules for who rides in that digital fast lane? It's a question that's only going to get more critical as we move forward. Thanks so much for joining me.